Okay, section 6.4 deals with best approximation and least squares. Okay, now if we consider this linear system where A is given by that matrix and B is that column vector there, then if we look at the system AX equals B, it's clear that this system is inconsistent. It's got no solution. Okay, so given such a system, now the question becomes, if the system is inconsistent, can I perhaps find a vector x that will bring me as close to satisfying this equality as possible? It will never satisfy it because it's inconsistent. But the question is, which values of x, or can I find an x, and if so, what does it look like? Can I find such a value x such that if I plug it in there, I bring ax very close to the vector b? And that's the least squares problem. So given a linear system ax equals b, where you are given m equations in n unknowns, we need to find a vector that minimizes the norm of the vector b minus ax. In other words, that's basically we're measuring the distance between the vector b and the vector ax, and we want to pick an x that will make that as small as possible. And this is with respect to the Euclidean inner product in Rm. So we call x, if x brings ax as close as possible to b, we call x a least squares solution of the system. And we call b minus ax the least squares error vector, because that indicates the distance that the vector ax lies from b. That's the error. And the norm of that vector is the least squares error. Right, so next up we've got an approximation theorem. It's called the best approximation theorem. So if W is a finite dimensional subspace of an inner product space, V, and B is a vector in V, then the projection of this vector B onto that subspace, orthogonal projection, that's the best approximation to B from the subspace W. And what they mean by that is that if you take any vector W in the subspace, then the distance between B and that vector W for any vector W in the subspace is always bigger than the distance between B and its orthogonal projection on the subspace. All right, and again, as I said, that needs to be true for all vectors W in capital W, and provided that W is a vector different from the projection of B onto W. So essentially, essentially the closest that this vector W will come to B, the vector B, that distance will always be bigger than the distance that B lies from its orthogonal projection on the subspace W. Okay, there we've got a schematic representation. So this is the subspace W, right? This is that vector there is the vector B bar minus W bar. That vector there is the vector W. This vector here is the orthogonal projection of B onto W. This vector here is B minus the projection of B onto W, which is that orthogonal vector there. And this vector here is a vector in the subspace W, and it is W minus the projection of B onto W. Okay, so basically this vector plus this vector here is going to be that vector there. Okay, write this vector here plus this vector here is going to be the vector B. Okay, and this vector here plus this vector is going to be that vector there. Okay. Now consider that colored part there. Remember this vector this vector here is orthogonal to W, right? So it's going to be orthogonal to this vector here. It's going to be orthogonal to that vector there. That underlined vector there is within the subspace W. And remember, this vector is in the orthogonal complement of W. Okay. So therefore, this implies that Pythagoras, we pretty much have that the norm of the vector, that vector there, squared, right, plus, okay, so again it's that vector there, plus the norm of this vector here, squared, is going to be equal to okay, so that is that vector there, is going to be equal to it's going to be equal to the square of this vector here. Right, which is that vector there. Alright, so therefore, right, now look at this vector here. We said initially that W is a vector other. It's a vector different from that vector there. So obviously, if you look at the norm, of this vector here, it's obviously it's not going to be 0. Okay, so that is going to imply that if we take that expression there and what we do is we pretty much we're taking on the left hand side of the equation, we're going to take that vector away, right? And then we've changed the equality, and we've actually made the left hand side smaller. So we have that, and so therefore we're going to have that the norm of this vector here is going to be smaller than the norm of the vector on the right hand side. Okay, so this vector W in the subspace, the norm, or the norm between those two vectors, the difference between those two vectors is always going to be bigger than the difference between the vector B and its orthogonal projection on W. Okay. And again, it doesn't matter what you make the vector w. This argument holds true for any vector w. So, therefore, that gives us a clue as to how we should choose a vector in the subspace that lies as close to B as possible. And the closest I can get is pretty much that vector. Right, so looking at this example, they ask us to find the best approximation of the vector B from the column space of A. Right, so we need to apply section 6.3 here, and we need to firstly quickly go and get a basis for the column space of A, and from there we can do the approximation. Right, so there we've got our vectors. Let's look at the column space of A. And remember how we do that. We take A and we go and reduce it. Right, we switch the first and the second row around. And from there we reduce it further. And then the last one we get 1, 0, 0, 1, 0, 0. Okay, so the columns with the leading ones are going to correspond to the basis column vectors. So therefore what you're going to have is you're going to take the first column, okay, and then you're going to take the second column, that's going to be your second vector, and so the basis, what I'm going to call it, is the basis for the column space, is going to be this set of two vectors. Right. Now, just note that this basis that I've constructed, if I look at the dot product of the first vector with the second vector, right, if I take that dot product, that's going to be 0. So what can I say? Because of that, I can say that the basis for the column space of this matrix it's an orthogonal basis. It's an orthogonal basis. So we can go back to section 6.3 and we can basically go and apply theorem. We can go and apply theorem 6.3.4, which says that we can go and we have a formula for the projection of the vector B onto this subspace W, where W is the subspace W is the column space of the matrix A. Okay, so we've got this projection that we can go and determine exactly because the basis for the column space is an orthogonal basis. So we need to go and firstly determine what is the inner product of the vector B with the vector V1, and that is pretty much going to be the dot product of the vector V1 with the vector B. Okay, and so that is going to be right, and that is going to be 2. Right, so the next one we're going to take B, we're going to take the dot product with the vector V2, and that is going to be right, so that is going to be -1. Right, so then the norm of V1 squared is pretty much going to be the dot product of V1 with itself. So that's going to be, and then the norm of V2 is going to be the dot product of V2 with itself. So that is going to be 1 plus 1, which is going to be 2. Right, so hence we've got that, and then we've got, okay, so that then becomes, alright, so there we've got the difference between the two separate vectors, and that then becomes, alright, so that's the least square solution to the linear system AX equals B. Right, next up we've got a few extra definitions. We call this equation, we call that the normal equation, or the normal system associated with the linear system AX equals B. So all you do is you multiply on both left and on right on the left hand side with the transpose of A. Now when viewed as a linear system, the individual equations are called the normal equations associated with AX equals B. Right, so it brings us to the following theorem. For every linear system AX equals B, this associated normal system is consistent. So it's got a solution, and all the solutions of one are least square solutions of AX equals B. Moreover, if W is the column space of A, and x0 is any least square solution of AX equals B, then the orthogonal projection of W is the orthogonal projection on W of B is going to be this vector AX0. Right, so let's look at that system. So why is it consistent? So what we can do is right, note that if we look at A's transpose, okay, and we multiply that with the vector B minus the projection of B onto the subspace that's formed by the subspace W. Is the column space of A. And remember, the column space of A, we can form a basis from the column space of we can form a basis for the column space of A. We can take a collection of column vectors of A, and that will we will be able to form a basis using the column, sum of the column vectors of A, some or all of them. So W, remember, is the column space of A. Then if we look at the product of those two matrices, that is going to be the it's going to be the zero matrix. And why is this? Because if you look at the column, if you look at the transpose of A, your columns are going to become your rows, right? And so you're going to multiply. So when you multiply this out, you're going to take the first row of A's transpose, which is the first column of A, and you're going to multiply it with this vector. Now remember, if we look at this vector, if you go back to your sketch, there's my sketch. Remember this, we said this vector is orthogonal to the subspace W. Okay. Now the subspace W is the subspace formed by the column space of the matrix A. Now remember, a certain number of those column vectors are going to be basis vectors. So therefore this vector here is going to be orthogonal to all those basis vectors, and therefore it's going to be orthogonal to every vector in the it's going to be orthogonal to every column vector of the matrix A. So that's going to imply that basically this vector is going to be orthogonal to every row vector of A's transpose. So it's going to be orthogonal to every column vector of A. And we know that the dot product, so if we take the first row of A transpose and we multiply it with the first column of this matrix, we're going to get 0. Right, now if we multiply that out, if we multiply the first column, we multiply the first row of A's transpose, which is the first column of A, with this matrix, with the first column of this matrix, we're going to get 0. And if we multiply the second row or the second column of A with this matrix here, then we're also going to get 0, and we're going to go straight through right up until the last row of A's transpose. And simply because of the fact that this vector here is orthogonal to every column vector of A. So we're going to get the 0 vector. So from there it follows then that A's transpose with B minus A's transpose with the projection of W, of B onto W, is going to be the 0 vector. And so from there we get that A's transpose B is going to be A's transpose multiplied by the projection of the vector B onto the subspace W. Now just let's consider the projection of B onto the subspace W. Now remember, I can, because the projection of B onto the subspace W is a vector within the subspace W, we can express this vector as a linear combination of column vectors of A. Right, so we can find values x1, x2 up until xn, such that we can express. Remember, some of these column vectors are going to form part of the basis. Right, so I can express the projection of B onto W as a linear combination of the column vectors of A. And so we can just express that as A multiplied by the vector x0, and this x0 is just the x0 is this vector here. It's the vector right. So going back, we can go and do the following. We can continue from where we left off, and we can do that replacement. So therefore, A's transpose B is equal to A's transpose, and we can basically replace that projection with that and that's going to imply that the system is consistent. If we take x0 to be a solution to that system, then we've got this situation here where that is the 0 vector, and this is going to imply that this vector here, this column vector, is orthogonal to every column vector of A. Right, so this thing here is orthogonal. So this vector is going to be in the orthogonal complement of the subspace W. So going back to our sketch, if we look at the vector B minus AX0, okay, that is a vector that is orthogonal to the subspace W. So it's orthogonal to every vector in the subspace. Now, if we add that to the vector, AX0, which lies within the subspace, that is clearly adding those two vectors together. That is going to be that vector there, and therefore we can see this now as pretty much the orthogonal projection of B onto W. So that is a least square solution of the system AX equals B. This x0 is a least square solution. Okay, so let's do this problem here. Here they ask us, let A be this matrix, and let B be that column vector. And then they ask us find all least square solutions of AX equals B, and just confirm that all the solutions have the same error vector. So now what we need to do is we need to take this system and apply the previous theorem. Okay, so there's my system. So all I have to pretty much do is I need to find solutions of A's transpose A, A's transpose B. So taking the transpose and then multiplying that with A, we need to then we need to find a solution to that system there. Okay. Right, so there we've got our two products that we calculated, which is this one and that one respectively. So that then basically becomes this system here. And therefore the general solution there we can easily go and determine that is Right, going back, we just need to also verify that all of the solutions have the same error vector. So we know the error vector is the vector b minus ax bar, where x bar is the solution, general solution. So that is going to be, if we look at the vector A, the matrix A, if we go and calculate the the matrix A, x bar, we get that, and that you can easily go and calculate as Right, so b minus ax bar is the same for all x bar in the solution space. Alright, so the next example here, find the orthogonal projection of b. So this question relates to the first question. On the subspace of R3 spanned by the vectors v1, where v1 is actually a column vector of A, and v2 is a column vector of A as well. So we're actually asking to find the orthogonal projection of B onto the column space of A. That's what we asked. Now if we go back to the previous theorem, if we look at the least square solution of the system AX equals B, which we found in the previous question, then we know the projection of B onto the subspace W, where W is the subspace formed by the column or the span of the what's the column space of A. It's simply the matrix A multiplied by X 0. Okay, so in the previous example, the least square solutions of this linear system was obtained. Right, so it is, we have these column vectors that we've taken, we form the matrix A, and then we establish that the least square solution to that system has this form. Of course, where t is any real number. Okay. Now what we are asked to find is the orthogonal projection of the vector B onto the subspace W. So by the previous theorem, the projection of B onto the subspace W is just a x0, where x0 is any least square solution. Right, so let's take a simple x. Let's just make t 0. Right, so this is going to be a solution. Right, so we've got this there. Right, substituting it in there in x0, and we get this matrix that we have to go and work out, and so we get from there we get the orthogonal projection of B onto the subspace W. It's the vector 11 over 14, 22 over 14, 33 over 14. Okay, that brings us to the next theorem, the uniqueness of the least square solutions. Right, so theorem 3 says that if A is an m by n matrix, then the following statements are mathematically equivalent. A has linearly independent column vectors, and A's transpose A is invertible. Right, so we need to prove if A is linearly independent column vectors, then A transpose A is going to be invertible, and if A transpose A is invertible, then we have to prove that A has linearly independent column vectors. And then also theorem 4 states that if A is an m by n matrix with linearly independent column vectors, then for every m by 1 matrix B, the linear system Ax equals B has a unique least squares solution. Okay, and the unique least squares solution is this solution here, because by the previous theorem, if A is linearly independent column vectors, then this matrix A transpose A is invertible. And by the previous theorem, you can just easily solve for x as that vector there. Moreover, if W is the column space of A, then the orthogonal projection of B on W is pretty much is this by the previous theorem, and you just plug that x value that you have here in there to get that. Right. Right, so to show that this matrix is invertible, we need to show that that system has the trivial solution by the equivalence theorem. In other words, we need to show that the vector x is the zero vector. Right, so let B bar be that column vector. B is a column vector, it's an n by 1 column vector, and A is an m by n matrix. Alright, now also let C1, C2 up until Cn denote the columns of A. Right, so you can then go and express B as a linear combination of the columns, or if you go and work that out. Okay. Right, so this implies that B is in the column space. It's in the column space of A. Let's call the column space of A W. That W is a subspace, right? Right, so there's W. It's the span of the column vectors, or the columns of the matrix A. Right, now if you go back to your original system, there we get that. That implies that A's transpose dot product with the column vector B is the zero vector. Right, and remember we said B is in W. And now the dot product between this, or rather the product between this matrix and that matrix is the zero matrix. Now what does this mean? This means that in the transpose the columns are not my rows. So if I go and work that out, if I work the entry in the first row and the first column of the zero vector, which is a column vector, it's going to be the first column of A multiplied by this first column vector, and that's going to be 0. And then you're going to take the second column of the matrix A, and you're going to multiply it with that column vector, and that's going to be 0 there. And you run through right up until the end, and you're going to get another 0 there. And this means that B is orthogonal. This means that B is orthogonal to every column for every column of A. And that's going to imply that B, because you've got, remember the column space of A, you find the column space, you can always find a few columns of A that will be a basis for the column space. And so B is going to be orthogonal to a basis, to all the basis vectors of a basis for the column space. And that's going to imply that B is going to be in the orthogonal complement of the subspace spanned by these vectors here. Okay? Right, so what is the implication of that? And now remember, if we go back here, remember the property of the orthogonal complement. That's going to imply that B is not only in W, but it's also in the orthogonal complement of W. So it's going to be in the intersection between the two. And we know the intersection between W and its orthogonal complement can only be the 0 vector, right? So it's going to mean that B is the 0 vector, okay? Right, now the fact that B is the 0 vector, if we go back to what B is, right? That's going to mean that is there the 0 vector, okay? So that whole linear combination is going to be 0 vector. And remember, we assumed that these are linearly independent column vectors, okay? So that's going to imply that x1 is equal to x2 is equal to, up until the very end, these are all going to be 0. And that's going to imply that x is 0. Back to your original system, that needs to be the 0 vector. And so by the equivalence theorem, this vector is going to be, or rather that matrix is going to be, it's going to be invertible. Okay, now going back, we just need to quickly show that if the transpose of A times A is invertible, then it is going to imply that A has linearly independent column vectors. So let's assume that matrix is invertible. What do we need to prove what? We need to show we need to show that A has linearly independent column vectors C1, C2 up until Cn. Okay, so let's suppose it is not the case. Then there exists values x1 up until xn such that Okay, so there exists this linear combination equals to the 0 vector for xi, a real number where I runs from 1 up until n, and we have at least one of these x's. At least one of these x's, say xj, the jth x, is not 0, because that means those column vectors are not linearly independent. So let's see what happens then. Right, so therefore, obviously, this is going to be true. Therefore, if I look at the matrix A and I multiply it with this vector x, where these x's are these values that I get there, it means that I can go and write that as a times that column vector, there. And also remember that we said that x0 is not the 0 vector, because at least one of these x's is not 0. So this is going to imply that A transpose multiplied by this is going to be A transpose multiplied by that, and so we're going to get that. It's going to be the 0 vector, and that is going to imply that A transpose A is not invertible, because we said that, remember, we assumed A transpose A is invertible, and therefore this system here, or rather, if we go back there, that system there needs to have only the trivial solution, but here I'm saying it doesn't have a trivial solution, it's got a non-zero solution there. So A transpose A is not invertible. And what is the problem with that? That is definitely a that's a contradiction. Right, so that can't happen. So those two statements are mathematically equivalent. If we consider this system and A has linear independent column vectors, then by this previous theorem we know that this vector or this matrix is therefore invertible. So what happens then is, what you can now go and do is you can take your system and you can basically go and multiply on the left with the inverse of this matrix, and what you do on the left you must also do on the right. Okay, and that you group together, and so that's going to imply that you can go and solve for your vector x as this quantity, this matrix here. And remember, guys, now be careful that you cannot now distribute this inverse over those two matrices, because remember, A and A transpose, they are not necessarily square matrices. We know the inverse is only defined over square matrices, but the product of A transpose with A, that is a square matrix. So therefore we can go and solve that x exactly. Right, so that is what this whole theorem is about. And by the previous theorem, we know that the projection of the vector B onto the subspace W, we know that that was previously AX, where X is a least square solution to the system AX equals B, right? But we've now solved this X exactly, and we can then just in there replace X with this matrix here, and we get that projection of B onto W. Looking at this example here, again, we are asked to find the least square solution of AX equals B, where A is this matrix and B is that vector there. Now, if you look at the column vectors of A, the column vectors of A, what happens if you take the dot product of the two column vectors? That's 0, right? So those two column vectors form a orthogonal set of vectors. And we said previously in section 6.3, we said that any orthogonal set of vectors is linearly independent. So those two vectors are linearly independent, okay? So by the previous theorem, right, so from here we have that the vectors, so we have that these two vectors are linearly independent. They are linearly independent. So by the previous theorem, what do, if we are to find the least square solution of this system here, that is going to be, according to the previous theorem, what did we solve? What did we solve it as? We solved for X as A's transpose with A. Multiply those two vectors together. You take the inverse of that. You multiply it with A's transpose, and then you multiply it with the vector B. So taking A's transpose and multiplying that with A is a straightforward procedure. You get that 2 by 2 matrix. Right, so therefore you're plugging that in. Then if you take the inverse of that matrix, that is going to be A transpose A's inverse, which is going to be 1 over 3 because it's a nice diagonal matrix, okay? And then multiplying that with A's transpose, we get. Right, then putting all of that together, that basically is now A's transpose A's inverse, okay, multiplied by A's transpose multiplied by the vector B. Alright, so multiplying those matrices out, we get this column vector 2 by 1, and that is then going to be, okay, so we get our least square solution of a third minus a half. Right, then lastly, just take note of theorem 5, which is an extension of the equivalence theorem. So now we just added one extra facet, which is this, that the matrix A transpose A is invertible. Now we know that ATA is invertible if and only if, though the matrix A has linearly independent column vectors. And so you can, that only happens, well, if A transpose A is invertible, then it's going to imply that the column vectors of A are linearly independent. And if that's the case, then A is going to be, that's going to imply that A is invertible. Okay, so all those conditions are mathematically